Hello everyone, welcome to my channel. Today I am going to talk about derivation of momentum equation or Navier-Stokes equation. So Navier-Stokes equation basically based on Newton's second law of motion. Ma is equal to F. M means mass, A is nothing but acceleration is equal to force. So in the Navier-Stokes equation, here is the Navier-Stokes equation. I'll derive this equation. So in the left hand side, that is nothing but mass into acceleration, and right hand side is the sum of all forces acting on the control volume or fluid particle, you can say. Now here is the problem statement of the Navier-Stokes equation. So here is the objective. So derive the governing equation for viscous fluid motion using differential control volume approach. Now here I am considering cubic differential control volume of size del x into del y into del z. Velocity field is V is nothing but Ui plus Vj plus Wk, and pressure field P of x, y, z and t. Here body force per unit mass, that F is nothing but Fxi plus Fyj plus Fzk. Now here we are going to find out the differential equation of the governing momentum conservation in x, y and z direction. Now here is the cubic differential control volume, that center is x, y, z coordinate, and here is the control volume properties. So it is in fixed pace, means it follow that Eulerian approach, and that cubic differential control volume has that del x length and del y height and del z width. So volume of the control volume is del x into del y into del z, and here that faces areas. So ax means that is the area, that is del z into del y. Similarly ay is nothing but del x into del z, and az is nothing but del x into del y. Now phase location and coordinates. So control volume geometry in the center located at point x, y and z. Dimension del x into del y into del z means del v, and fixed in pace means Eulerian approach follow, means fluid flows through control volume. Now here phase center coordinate. So here this is x, y, z coordinate. So now from here to this phase, that distance is del x by 2. So from here to the left hand face, that distance is del x by 2. So now if this is x, so this face the coordinate will be x minus del x by 2. This face coordinate will be x plus del x by 2. So here face center coordinate, x face means west at x minus del x by 2, east at x plus del x by 2. Y face south at y minus, similarly in y direction y minus del y by 2, north at y plus del y by 2, and z faces bottom at z minus del z by 2, top at z plus del z by 2. So face areas again, that ax is nothing but del y into del z x faces, ay del x del z y faces, and lz del x del y z faces. So what is the purpose for that? Each phase pair will be analyzed for momentum flux and forces to derive differential equations. Now here the differential momentum conservation for differential control volume, accumulation plus net efflux is equal to applied forces. So here is the mathematical form. So dou rho u by dou t into del v plus net momentum flux is equal to sum of all forces. Now here is the component, means accumulation means rate of x momentum storage in a control volume, so that is, and then x momentum carried away by fluid motion through phases, so that is net momentum flux or efflux. And forces, here one is body forces acting on the fluid element, another that surface force, here two surface force acting on the fluid element, one is pressure, another is viscous force. Now here I'll talk about rate of momentum accumulation term. So physical concept, how fast x momentum. Now here I am considering only x momentum. So from here I'll get that x momentum conservation equation. Similarly we can get y and also z. So x moment, so here physical concept is how fast x momentum builds up inside the control volume over time. So here is the mathematical expression in temporal term, dou by rho u dou t into del v. So dou rho u by dou t nothing but del x del y and del z. So now here detailed term explanation. Rho is nothing but fluid density, u is x component of velocity, rho u is nothing but x momentum per unit volume, and dou rho u by dou t is nothing but rate of change of momentum density, and del v we know del x into del y into del z, that is control volume. Now here is a physical interpretation. So if dou rho u by dou t greater than 0, so x momentum increase in control volume. If less than 0, so x momentum decrease in control volume. And if dou by dou t of something is 0 means steady flow, no local acceleration. So local acceleration will be 0. You can check the unit. So units is actually Newton. Now here is the momentum flux concept. Now here we considering one face, and that face has area A. Now from this face the momentum flux through this face is uh, that flux is nothing but momentum density into velocity into area. So here x momentum is going out from this face, so that is rho u means that is momentum density, and then velocity with velocity v into area. So rho u into Vn into area. So Vn is the velocity component normal to the face. So now here is the fundamental concept. So momentum flux is nothing but rate at which momentum flows through a surface. So already we know the momentum flux, momentum density into transport velocity into area. So here momentum density is nothing but rho u, transport velocity Vn, that is normal to the surface, and A is the area. So here detailed term analysis, rho u x momentum per unit volume, rho is nothing but mass density, u is x velocity component. So product gives momentum concentration or momentum density, and Vn is the velocity normal to the face, so speed at which fluid cross the faces, that determine transport rate, and A is the face area means surface through which momentum flows. Now physical analogy. Now if you compare with physical things, so like people carrying a bag through a doorway. So bag, the rho u is nothing but bag per person. So that is momentum is each carries. Now Vn is walking speed through the door. Okay, so that man is walking through the door. So man walking speed, and A is the door area. So flux will be total bags flowing through per second. So again units if you verify, that is also Newton. So now here x momentum flux through x faces. So here is the control volume. So this is left face and this is right face. So now here, so everything is in the center. So here the coordinate is x minus del x by 2. Right hand side coordinate is x plus del x by 2. And rho u square means the u is x momentum density component. Second u is nothing but transport velocity in x direction. So remember that first u is momentum density component, second u is the transport velocity in x direction. So rho u square is nothing but rate of x momentum transport per unit area. So let left face in means rho u square left into del y into del z. So that will be x momentum flux in the left face. Right face flux is rho u square, the del y into del z. So net flux will be right minus right side x momentum flux minus left hand side x momentum into del y into del z. Now again, so expanding around center point, so x y z, so rho u square L will be rho u square minus dou rho u square del x plus del x by 2 using Taylor series expansion. So right face will be rho u square R is nothing but rho u square plus dou rho u square dou x by del x by 2, like f0 fx0 plus h is nothing but f of x0 plus h dou f by dou x, okay, plus higher order term. Okay, so now here we are taking only two term. So here rho u square L is nothing but rho u square minus dou rho u square by del x, dou x into del x by 2. So here minus means left hand side, here plus positive in right face because of coordinate. So net flux through x face is nothing but right minus left. So we'll get the dou rho u square by dou x into del x del y into del z. Similarly, so x momentum flux through y faces, so we will get net flux through y faces will be net flux y dou rho v u by dou u del x del y into del z. And for this similarly z phase, so net flux z will be dou rho w u dou z del x del y del z. So total convective term for x momentum flux will be dou rho square by dou x plus dou rho v u by dou y plus dou rho w dou z into volume. So now we got that left hand side part. Now right hand side means mass into acceleration we got. Now we have to calculate sum of all forces. Now here is the body forces. First consider control volume. That rho g is acting on the total control volume, means body force act on the entire fluid mass. So Fx body is rho into volume, that is mass, into Fx means acceleration. So here Fx is nothing but minus g, means if x points upward. We can also consider electromagnetic force or centrifugal force, but here we are not considering, only gravity force we are considering as a body force. Now pressure force. So pressure force on individual force, again we are taking control volume. So this is left face and this is right face. So left face force F left is plus that PL del y del z. So act rightward into that CV, and right face that F right minus PR del y del z acts leftward into the CV. So pressure always acting inward to the surface. So here that this is that PL into that surface, and here sorry PL into that surface and PR into right hand side surface. So it is the negative x direction, so that's why minus sign is coming. Now the net force calculation, so F left plus F right, so we'll do that. So that will be PL minus PR into PL minus PR into del y del z. Now if we do the Taylor series expansion, so again PL will be P minus dou P by dou x del x by 2, right face pressure that PR, that is nothing but P plus dou P by dou x del x by 2. Now substituting Taylor's expansion, so finally FPX will get minus dou P by dou x del x del y and del z. Now here physical meaning of negative sign. If dou P by dou x greater than 0, pressure increase in x direction. So higher pressure on the right face pushes fluid leftward, so that is negative x direction. So here that Fpx is minus dou P by dou x into del V, negative signs, means left fluid will move to the rightward direction. Now here we'll talk about, so body force we already we talk about that, then pressure force, surface force. Now another surface force is that viscous force, or that is the stress. So I'm going to talk about stress tensor. So here 18 component of the stress tensor are there, so that acting on the different faces, means each faces three the stress actually acting. One is normal, another two is that horizontal or shear stress. So trace component from the face center, so x face left to right, so tau xx, tau yx and tau zx. So here tau xx is normal, tau yx is y shear, and tau zx also z shear. We'll talk the details what is the meaning of tau xx, tau yx. Sometimes we can also write that sigma xx, sigma yx, sigma zx. And y faces front and back, that is tau xy x here, tau yy is normal, and tau zy is z here, and z faces bottom and top, tau xz x here, tau yz y here, and tau zz normal. So you can see that picture how it is acting, you can get from this picture. Now total 6 faces into 3 stress by its per face, so 18 stresses components complete stress tensor component. So we can write in the matrix form, tau is equal to tau xx, tau xy, tau xz like x y z, and again x y z, tau yx, tau yy, tau yz, tau zx, tau zy, tau zz. So notation here is tau ij is nothing but stress in I direction on face with normal j direction. And symmetry properties uh, follow for this test tensor. So tau ij is nothing but tau ji, so that is actually called momentum equilibrium. So only 6 independent component we have to consider, that is 6 independent component we have to consider. All are that shear stress, and another 3 in the diagonal all are normal traces. Now here trace component on the x face. So we are taking two faces. Now we'll show here it is showing how that trace component coming out from this one face, that is x face. Now here is the physical meaning of the x direction stress component. So tau xx, so that is normal trace on x faces. So definition is stress component in x direction acting on faces with normal in x direction, type normal stress that is perpendicular to the face. And tau xy shear stress on y faces, stress component in x direction acting on force faces with normal in y direction. So that is shear stress parallel to the faces. You can see here. So one is that is the normal to the face, other two are parallel to the surface. Now physical effect causing sliding or shearing deformation in x direction, and cause velocity gradient dou u by dou y means x velocity changes across the y direction. And tau xz, that is shear stress on z faces. So shear stress component in x direction acting on faces with normal z direction. So shear stress again that is parallel to the face, cause sliding or shearing deformation in x direction. So velocity gradient dou u by dou z, x velocity changes across the z direction. So key insight is here, all three components contribute to the total force in x direction on the fluid element. Now here I told you that we can write that tau xx in terms of sigma xx, this is also sigma xy, and this is sigma xz. We can write that. Now if you consider in this phase, suppose sigma xx, tau xz, tau xy is acting, so what will be here? If you know this force in that phase, so and distance is that is del x, so in that side will be by Taylor series expansion it will be sigma xx plus sigma dou sigma xx by dou x into dou x. You will get that this is the Taylor series expansion. Similarly for other also, so like here that is tau xy, so it will be tau xy plus dou tau xy dou x plus that delta x. So now here in that 6 phases, so here the three, so sorry, in that x this phases 3 that shear force, sorry, 2 shear force and 1 normal force is acting. So here x component of the net shear force acting on the cubical volume of particle is computed as follows. So x component is sigma xx plus dou sigma xx by dou x by del x minus that sigma xx. So for this is acting this direction, this is acting this direction, so we have to make the negative, so that will get one component. So then so this component will be sigma yx plus and that dou sigma yx dou y into that delta y minus sigma yx into del x del z. Similarly sigma zx plus dou sigma zx dou z by dz delta z minus sigma zx into del x del y. So we'll get the x component. So now from here this will be cancelled out, we will only get that dou sigma xx dou x into del x dou sigma yx dou y delta y into del x del z and dou sigma zx del z into dou z by into del z delta x delta y. So now finally we'll get any x component dou by sigma xx by dou x plus dou sigma yx plus dou sigma zx by dou z into del x del y del z means volume. So x component of the net force acting per fluid element of volume dv is computed by dividing del x del y and del z. So x component net force per unit volume will be dou by, so here net force per unit volume will be dou sigma xx by dou x plus dou sigma yx by dou y plus dou sigma zx by dou z. So we'll get the x component. Okay, similarly we can calculate that y component and z component. So it will be, if we take all together, so that will be divergence of stress tensor. So we'll get, so divergence of stress tensor is computed as follows, so that x component, y component and z component, we can get that. Now here we are considering only x component, so similar way if we do that, we will get other things also. Now momentum conservation, so accumulation plus net flux is equal to body force plus pressure force plus viscous force. So we got the accumulation, so that is dou rho u dou ty into delta v plus this is the net flux we got. Body force is equal to body force, then negative pressure force and then viscous force. So dividing by del v, so we'll get dou rho u by dou t plus dou rho u square by dou x plus dou rho vu by dou y plus dou rho wu by dou z is equal to rho fx minus dou p by dou x plus that delta dot tau x, or you can say, sorry, not delta, nabla dot sigma. So we did that in earlier, so that here we can write tau is nothing but sigma. We can write either tau or you can write sigma. So this is a Navier-Stokes equation. Now here simplification using continuity equation. So we know that continuity equation dou rho by dou t, that nabla dot rho into v is equal to 0, that is continuity. Okay, and we can also write that dou by dou of rho u by dou t plus that nabla dot rho uv is nothing but rho du by capital dt. So where dou capital du by dt is that material derivative of substantial derivative, so that is nothing but dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. You have to remember that. Now here, so simplified form, so we got here, so if we do the simplification, so we'll get this is nothing but rho dou u by dou t. So from there we can write that rho dou u by dou t is rho fx minus dou p by dou x plus dou tau xx dou x plus dou tau yz by dou y plus dou tau zx by dou z. Now here from Newton law of viscosity, if we plug that velocity, so that will be, so constant viscosity and incompressible flow, so we can write that rho dou u by dou t plus rho fx minus dou p by dou x plus mu del nabla square u. Okay, and we know that material derivative is nothing, dou capital du by dt is nothing but dou u by dou t plus v dot nabla into u. Now vector form for the incompressible flow, so here that viscosity and density is not a constant, so that will be rho dou v, so this is vectorial form, dou v by dou t plus v into nabla into v is equal to rho f minus that nabla p plus mu or grad p the nabla square v and plus continuity equation nabla dot v is equal to 0. So here this is nothing but local acceleration, and v dot nabla v, that is convective acceleration, and that del p, if I take that rho in that side, so that will be rho, that will be rho, and that will be rho. Okay, so that f, this is del p by rho, that is pressure for per unit mass, and mu, that nabla square v by rho, that is viscous force per unit mass. You can, this is the physical meaning all this term. Now in the x direction, so we'll get that rho, that capital Du by capital Dt is equal to rho gx plus that dou sigma xx by dou x plus dou sigma yx by dou y plus dou sigma zx by del z. Similarly, we'll get y direction component and z direction. So now these are the detailed equation for each direction. So we plug that dou capital Du by dt in terms of velocity, we'll get that equation for each direction, x direction, y direction and z direction. Now if I plug velocity term in normal stresses and shear stresses, so final equation will be rho dou u by dou t plus u dou u by dou x plus v dou u by dou y w dou u by dou z is equal to rho gx minus dou p by dou x mu dou square u by dou x square dou square u by dou s square dou square u by dou z square. So similarly you will get the y direction and z direction. Remember, so here u all are changing, so that's why it is a x momentum equation. Okay, so here gx and this is x. Now for y, so you change that u to v and here x to y, this is x to y and these all will be v, so that will be your y momentum equation. Similarly again if you change u to w, so that will become that z direction equation, momentum equation. Now complete Navier-Stokes equation and detailed component analysis. So vectorial form is rho dou v by dou t plus v dot nabla v is equal to rho f minus that grad v plus mu into nabla square v. So left hand side that acceleration term, that is Newton per meter cube. So here that is force per meter cube. Remember that Navier-Stokes equation, if the rho is here, so that will be force per meter cube. So these also a force per meter cube. Remember that. So rho is fluid density and dou v by dou t is local acceleration. So rate of velocity change at fixed point in space. So unsteady effect mean time dependent flow. And v dot nabla into v, that is convective acceleration. So that is nothing but u dou v by dou x plus v dou v by dou y plus w dou v by dou z. So that is acceleration due to the fluid moving through non-uniform velocity field. And here this is the nonlinear term is coming. Nonlinear term make equation difficult to solve. So in the Navier-Stokes equation is highly nonlinear. So nonlinearity is coming from this term. Okay, so that's why it is very difficult to solve. Now right hand side, that rho into f, again this is force by unit volume. So body, that rho f is that body force per unit volume. So f body force per unit mass and rho g is the example. And again minus grad p means pressure gradient force, that is nothing but dou p by dou xi plus dou p by dou yj plus dou p by dou zk, and mu the nabla square v viscous forces. So nabla square v is nothing but dou square v by dou x square dou square v by dou y square plus dou square v by dou z square. So that is Laplacian, and mu is the dynamic viscosity Pascal second or kg per meter second. So that is diffuse momentum for the smooth velocity variation. Okay, so here this is body force, this is pressure force, and this is viscous force. So now these are the each term of the Navier-Stokes equation, that is a complete form. So now here is the summary. So summary: differential control volume approach, define cubic CV with phase at plus minus del x by 2 etc. Apply momentum conservation directly. Calculate momentum flux through each phase using Taylor's expansion. Include all forces: body force, pressure force and viscous force. Take limit the del v is equal to 0 to get differential form. Use content equation to simplify. Now here result: complete nonlinear PDE system governing viscous fluid flow. So here 4 equation and 4 unknown. So 3, here you can see that. So these are the 3 equation along with plus continuity equation. continuity equation. So means 4 equation and 4 unknown means u, v, w and p. And nonlinear PD is due to the convective term. So you remember that the Navier-Stokes equation highly nonlinear because of that convective term. And key insight, each term emerges naturally from physical conservation principle applied to differential volume. So that's about Navier-Stokes equation. Thank you for listening.